So, first thing, when we talk about computer output, so you've seen some throughout some of the questions in chapters 1 and 2, some in this chapter even a little bit earlier on. But we're going to talk about how to make sure we know how to read these. So how do we locate the information that we actually need? So when we're talking about regression analysis, so they plugged it through some particular software. That software gives them an output. We need to know how to read it. So how do we find our slope? How do we find our y-intercept? How do we find our correlation squared and our standard deviation? So when you're looking at a software output, you need to be able to find these 4 things because we're going to be asking questions about what is the equation of the line. And in order to get the equation, you need to know what the slope and the y-intercept are. They may ask you to interpret the standard deviation or interpret R squared or report those particular values. You need to know where to find those in the output. So when we look at the different software packages, for the most part, they all put out the same looking table. So it all looks extremely similar, all has some of the same things in common. So when you see a computer output, it's going to look something like this. So they're going to have a list of what they actually talked about. So the predictor, that's just talking about the y-intercept and the slope. Okay? So you have the constant here. It's telling you everything you need to know about the y-intercept. So constant is always labeling the y-intercept. Then underneath that, they're always going to give you the actual name of one of the variables, and that's going to be the x variable, which means this is going to be our slope. So everything in this top row pertaining to constant is talking about the y-intercept. Everything in the second row, talking about miles driven in this particular instance, is talking about the slope. So in the next column, they're telling you the coefficient, that COEF is standing for coefficient. So this value, this 38,257, that's the actual value of our y-intercept. 0.16292, that's the actual value of our slope. So that first column tells you which variable you're looking at, or which piece you're looking at. Are you looking at the y-intercept, or are you looking at the slope? Okay, constant's y-intercept, named variable is slope. Second column is going to give you the actual values. So that's where you're going to get your information to create your regression line and so on. The rest of the stuff in these rows is not useful to us yet. We'll talk about that stuff later on down the road. For right now, since all we know how to do is work with a regression line, these are the only 2 pieces we definitely need to make sure we can find in this output. The rest of this stuff, standard error, the t-value, the p-value, that stuff will come much later down the road. Okay? So for right now, the big thing, can you find y-intercept, can you find slope? Okay? The other ones then are going to be your standard deviation and your R squared. So your residual standard deviation, that's going to, most of the time, just be labeled with a simple S. So it's going to be something kind of on its own within the output, S equals whatever. R squared is generally not going to be written out in notation form with the little r squared. It's going to be actually written out probably in words or something like this with abbreviations. So R squared there is going to be reported that way. And it'll generally be reported as a percentage because that's how we report it when we interpret. Okay. So if we were given this particular output and it said, what is the equation of the regression line? What would we write? How would we write our equation based on the information in the table here? How do I write a regression line equation? So 0.16292 x. So Slope always goes on x plus 38,257. And what's this going to equal? Y hat. Okay, so if they ask for the equation of the regression line, you just pull the two pieces of information, slope, y-intercept, and just plug them in for your x and your constant. Okay, and then don't forget, when we write our regression equations, it's always y hat. It's a predicted value, not an exact value. We okay with that? So standard deviation and r-squared, those are usually pretty easy to find because they're labeled outright. This is standard deviation, this is r-squared. The ones that people tend to get mixed up are y-intercept and slope. So it's important that we understand constant always refers to y-intercept. Named variable always pertains to slope. And so then it's all just a matter of taking the coefficients here and plugging them into your regression equation correctly. We okay with that? All right. So that's it for computer outputs. They're all going to look almost identical to that every time, so it's just a matter of finding the pieces you need and reporting what you want for those particular pieces. All right, so outliers and influential points. Now, when we create our regression line, or what we can call the least squares line, we are trying to make the sum of the squares of the vertical distances to the points as small as possible. So remember last week we talked about when we have a scatter plot, okay, so something like this, we draw our least squares line through it, something like that. And we talk about the fact that that line is not going to pass through every point. In fact, a lot of times it may not pass through a single point that we have in our graph. Okay? So each of these points, we would measure the distance from the point to the line, which is measuring what? What would all of these vertical distances from the point to the line be? The residuals. Okay? So if we measure all the vertical distances from the point to the line, and we square those residuals. So if we take every single residual and square it and add them up, our line should be created in such a way that it's going to be the smallest we can possibly get. So whether we try to move that line anywhere else, that sum is going to get larger if we move it. So we're trying to find the exact spot that passes through the points so that those distances are as small as possible. Okay? So that's the goal behind that least squares regression line. Make those vertical distances as small as possible. Now, if we have outliers, and outliers can happen in a couple of different ways. A point that is extreme in the x direction with no other points near it is going to pull the line towards itself. So if we have a value that's really large in one direction or the other on x, okay, so it could be something like this. So we have this cluster of points down in the bottom left here, and then we have this one extreme value that has a way higher x compared to any of the others. Or it might be something that we have all our data here, and we have one that has a really small x value compared to all the rest. Okay? And it doesn't necessarily have to line up with the information. It could be something that's up here, or something that's down here. It's just something that has a very large x value compared to the rest, or a very small x value compared to the rest. When that happens, and there are no other points around it, that point is going to pull the line towards it. So wherever it happens to be, that line is going to get yanked towards that particular point. So if we had an original line here, this high point up here is going to pull the line closer to it. Or if we have the point down here, that's going to pull the line closer to it. So those values with large or very small x compared to the rest of the values is going to yank the line towards it. That's what we call an influential point. That's one of the definitions. Okay? Now, the other way to think of influential points, so when we talk about whether a point is influential for a certain measure, is to think about, if we remove that point, will we drastically change the result? So we consider points to be influential for a given calculation. So maybe calculating mean, maybe calculating correlation, calculating slope and y-intercept. So a point will be influential if removing that point would markedly change the result of the calculation. Okay. So if we're looking at a scatter plot here, so they're comparing the age at which a kid first speaks or speaks their first word in months and a score on a given test, like an aptitude test for kids. So they're trying to compare the two values there. Okay. So we notice that most of the children have information right in this big cluster here. And then we have 2 points, 2 children that kind of lie outside the norms. We have child 18 way up here, and we have child 19 lying above our pattern there. Okay, so both points would be considered outliers. There's something strange about those particular points here. Okay, so child 18, for instance, what's unusual about them? Yeah, how old they were when they said their first word. All the other kids in the study were somewhere in the probably like 8 to 20 months range. This kid didn't speak their first word until they were 40 or 41 months old. So that's an unusual value. Okay? Now it just so happens that that point lies somewhat within the pattern of the original clump, right? So this cluster of points here looks like it has kind of a linear negative association, and it tends to line up a little bit with that child 18. So it's an unusual point that just happens to line up nicely. What's unusual about child 19? Yeah, the score on their test. So for how old they were, when they spoke their first word, right around 19 months, 18 months or so, they scored way higher on that particular test than other children that spoke their first word at around the same age. So they scored a much higher exam score than others around their same age. Okay? Now when we look at this, we can also notice the residual plot here. So child 18 and child 19, they're both outliers. But when we look at those outliers, as far as residuals go, they may have a very small residual. Like we said, child 18 lines up pretty nicely with the rest of the data. So when we look at the residual plot, child 18 is not going to have a very big residual. The line's going to be pretty close to predicting that score. Whereas child 19 was a different type of outlier. When we look at child 19, it was in the right spot for X, but the wrong spot for Y. So we're going to see that it has an unusually high residual compared to the rest of the kids at that particular point. Does that make sense? So when you're identifying outliers, they can happen one of two ways. Either they're going to have a very large X value, or a very small X value compared to the others, or they're going to have a very large or small Y value compared to the rest. Okay? So when we talk about outliers, we're not basing it on how close they are to the line. That's one of the things we have to make sure we understand here. It's not whether it's an outlier based on how close it is to the line, it's how it relates to the rest of the data in our set. So child 18 and child 19 would both be considered outliers. One has an unusually large x value, the other has an unusually large y value. Okay. Now, if we kind of start looking at how things change as we remove or add in those children's scores, okay, notice with all the children in, okay, so with all 19 children accounted for, our correlation would be negative 0.64. Our regression line would have a y-intercept of 109.874 and a slope of negative 1.127. That's with everyone accounted for. Okay. Now, if we remove child 19, so if we get rid of child 19 up here, our correlation jumps up to negative 0.76, and we also get a slightly different equation as far as our y-intercept and our slope. So notice, as far as influencing goes, was child 19 influential on the correlation? So when we removed child 19, did correlation change by quite a bit? Yes, it did. Okay, it went from negative 0.64 to a much stronger association of 0.76, negative 0.76, right? So it was influential on the correlation. Was child 19 influential on the regression line? So on the y-intercept or on the slope? Not really, right? So when we took out child 19, nothing really changed drastically for that. So it's not influential on the actual equation of the line. It's going to be the same either way, but it affected correlation. Okay? Now notice if we take out child 18. So child 18, did it affect correlation? Yes, it did. By getting rid of child 18, now we give child 19 a lot more influence as far as how strong our correlation is. So taking it out became influential. It changed drastically that value of for our correlation. What about for our regression line? That our regression line changed drastically when we take out child 18. Quite a bit, okay? So instead of up at 109, now we're crossing the y-axis at 105. Instead of a slope of negative 1.1, we're now at negative 0.779. So in the grand scheme of things, that's quite a drastic difference between what we had with child 18 in and what we had with child 19 out. So when it asks about whether something's influential or not, that's what you have to take into account. If we remove that point, does that particular calculation change based on that? Okay, so child 18 was influential for everything. Child 19 really only influenced correlation. You okay with that idea? So outliers may or may not be influential points. You have to take a look at what happens when we remove those particular points. Okay. Last thing, just kind of some last minute review stuff. The distinction between explanatory and response variables is very important. So we talked about that last week. Once we start looking at regression lines, knowing which one's explanatory, knowing which one's response is going to be very important, because when we calculate our regression lines, if we flip-flop, we're going to be changing correlation not at all. So flip-flopping x and y doesn't change correlation, but it drastically changes the equation of our regression line. So notice in our first scatter plot here, we used miles driven as the explanatory and the price in dollars as our response. So when we look at our equation, our predicted price would be 38,257 minus 0.16292 times the miles driven. Notice what happens if we flip-flop x and y. So now we have price in dollars on x, miles driven on y. So all we've done is change where x and y are. Now we get an equation, so the predicted miles driven will be 177,462 minus 4.0772 times the price. So the equation is completely different because x and y changed. But what do you notice about r squared? It's exactly the same. X and y is not going to affect correlation, which means it's not going to affect correlation squared. So when you're doing the regression line, make sure you have your x and y located correctly. Otherwise, you're going to get drastic differences in your answers for the equation of the line. Okay. The other thing, I know we mentioned this a lot last week, correlation can only be utilized if we are working with linear associations. Okay. When we look at these four graphs here, which one or ones would we feel comfortable using correlation for? Okay, so A for sure, C probably, but what would we have to kind of maybe take into account there? Yeah, we do have an outlier we'd have to kind of analyze and maybe discuss, right? So we'd be a little hesitant there because we know correlation is not resistant, so that outlier is going to affect it, right? So what happens here, these four graphs, the only one we'd probably want to use correlation for and not have any reservations would be part A. It's got a linear positive association. We can use correlation to denote the strength between those two variables. But if we look at these four graphs and we actually calculate correlation, they would all come out to be identical. For these four different data sets, they all look quite a bit different. They all come up with the same correlation coefficient. So if you calculate correlation without looking at the scatter plot, you might be getting some information that doesn't really make sense. Okay? So it only works for linear associations. The other thing, all four of these graphs would generate the exact same regression line. Same y-intercept, same slope. So even though things are non-linear, you can still plug it in your calculator. Your calculator can fit a line to it, but if it's not a linear association, that line doesn't mean anything for us. So always check to make sure you have a linear association first before you start messing around with correlation and before you start messing around with your regression line. Okay? With that, even if you look at the scatter plot and assume it's linear or you think it looks linear based on what you're looking at, what should you always check just to make sure before you do a linear model, or to check your linear model, make sure that it's appropriate? Besides the scatter plot itself, what else should you check? What was the other type of graphical display we talked about last week? The residual plot. So if you look at your scatter plot, it looks linear. You can fit a line to it. But once you fit a line to it, you need to check the residual plot to make sure you didn't miss any curve or nonlinear nature to that particular scatter plot. Okay, so depending on your scales might have hidden some curve in there that the residual plot would pick up. So you need to check your residual plot, make sure it is truly linear. Okay? That's it. It's the last little bit of chapter 3. So I want you to try these problems out.
Give those chapter
The 3?
Yeah.
Yes, at some point. I still have 2 or 3 people I didn't make it up. They're in the grade book, so you can see how you did, but yeah, we'll go back to 3rd. We'll probably Probably the plan will be till today. You got a lot of time right now. I would just use this time to work on the assignment. So if you're still finishing up page 193 or you want to start working through this, start working on this stuff, ask questions if you have any. Tomorrow during the homework day, what we can do is if you want to see or go through the rest of your test, we can kind of do that on an individual basis. And then hopefully if I can get these made up in the next couple of days, like during one of the review days or something, we'll go over the quiz as well, so you can kind of see how you did there, what you missed, and go with that. So we got lots of time over the next couple of days to see those.
I've seen the scattered on my sheet and I can't find it in my folder.
Did you didn't turn it in?
I don't think so.